The realization that the cosmos and creation itself did not revolve around humans was first shown by the Andromeda Galaxy. It provided evidence that there are other galaxies outside the Milky Way and that we might only be a tiny dot in the larger cosmos. Although we have come a long way in the last century about Andromeda, the majority of our knowledge has come from Earth. Things are very different now that we have tools like the James Webb Space Telescope at our disposal. The Andromeda Galaxy is not what we formerly believed it to be. The whole scientific community has been astonished by data from the James Webb Telescope. Come along as we reveal to you the full truth about the Andromeda Galaxy and the startling discoveries that have taken us a century to realize. What if the entire scope of our knowledge about this galaxy and the universe is about to shift? When the Milky Way was first discovered a little more than a century ago, people's perceptions of it were varied. They often associated it with the center of creation, where the celestial and terrestrial spheres met. This view was influenced by the limited technology available at the time, which prevented astronomers from distinguishing individual stars within the Milky Way. The Milky Way was thought to consist of a vast collection of individual stars, planets, and other celestial objects. The nearest galaxy to us is the Andromeda Galaxy, and it is estimated that there are about 100 billion galaxies in the visible universe. Galileo Galilei, an Italian astronomer, revolutionized our understanding of the Milky Way in the early 17th century by using his newly developed telescope to make groundbreaking observations that challenged the prevalent Aristotelian cosmology. In 1750, English astronomer Thomas Wright put forth a novel hypothesis in his work, An Original Theory or New Hypothesis of the Universe. In it, Wright postulated that the Milky Way was not a randomly distributed starry sky but rather a flat layer of stars, and that our solar system was a part of this vast structure. Although Wright's hypothesis advanced our understanding of the Milky Way structure, it was still constrained by the observational technology of the day, and many people continued to believe that the Milky Way was all there was to the universe at that time. A belief that makes sense given the limitations of the time. By the early 1800s, astronomy had advanced significantly, and by the early 1900s, things were changing quickly. In the 1920s, American astronomer Edwin Hubble made a groundbreaking discovery when he used the 100-inch Hooker telescope at Mount Wilson Observatory to observe far-off nebulae beyond the Milky Way. By analyzing and observing these objects, Hubble demonstrated that they were actually completely separate galaxies, each containing billions of stars. One of the closest of these galaxies was the Andromeda Galaxy, or M31. The Andromeda Galaxy has a long and illustrious history of observations. It was first noted as a small cloud in star charts from the 10th century by the Persian astronomer Abd al-Rahman al-Sufi. This moniker came about because al-Sufi was able to identify this far-off cosmic entity without the aid of telescopic instruments. Instead, he relied solely on his keen eyesight and observations. This makes Andromeda one of the few galaxies in the universe that can be seen from the surface of Earth without the need for special instruments. You just need to know exactly where to look to see it in the open sky, and even though you can't see much detail, you can still tell that something other than the usual stars is present. It wasn't until 1612 that Simon Marius gave a more thorough description of the Andromeda Galaxy based on telescopic observations. His work laid the groundwork for later astronomers to study this massive cosmic structure. Later, in 1764, the famous French astronomer Charles Messier catalogued the Andromeda Galaxy as M31 in his well-known Messier catalogue. Messier incorrectly attributed its discovery to Simon Marius, unaware of al-Sufi's earlier work, but Messier played a significant role in putting Andromeda on the map. For nearly a century afterward, astronomers from all over the world attempted to learn more about this mysterious galaxy, building on the discoveries of their predecessors. Andromeda is a massive cosmic structure with a mass estimated to be between 1 and 2 trillion times that of our Sun. It resides relatively close to us in the vastness of space. Based on research conducted thus far, scientists believe Andromeda is about 10 billion years old, making it quite ancient in cosmic terms. This age hints at a long and intricate history of formation and evolution. A significant leap in understanding the nature of the Andromeda Galaxy occurred in 1864 when the English astronomer William Huggins made a groundbreaking observation regarding the galaxy. The idea that Andromeda originated by combining a number of smaller proto-galaxies is one of the more intriguing aspects of its formation. It implies that over billions of years, smaller galactic entities gradually came together under the influence of gravity to form the magnificent Andromeda Galaxy that we see today. These kinds of galactic mergers are common in the universe and shape the structure and growth of galaxies, but they occur so slowly that it is nearly impossible to observe the process in real time. Only significant changes over extended periods of time become visible. Astronomers mistakenly believed for a long time that Andromeda was much larger than our galaxy, the Milky Way. This is understandable from an observational point of view, since Andromeda is inside our galaxy and is difficult to measure accurately, and it appears so large from Earth that nothing could possibly match its scale. Nevertheless, new findings have caused scientists to rethink their assumptions, somewhat lowering their estimate of Andromeda's mass while simultaneously increasing the mass attributed to the Milky Way. Although opinions on the mass of Andromeda differ, scientists are more in agreement about its physical dimensions. Andromeda is larger than our Milky Way, with an estimated diameter of about 220,000 light-years, exceeding the Milky Way's estimated diameter of roughly 100,000 to 175,000 light-years. Because Andromeda is so large and occupies a significant area of space, it is a truly significant cosmic entity. However, measuring the mass of galaxies is still a challenging task because galaxies are massive systems whose masses depend intricately on the distribution and movements of stars, gas, dust, and dark matter. Precisely determining these values requires advanced observational methods and careful analysis, both of which were unavailable in the 1700s or even 1800s. The active galactic nucleus, AGN, of the Andromeda Galaxy is one of its most intriguing features. An AGN is a highly energetic region at a galaxy's center that is characterized by intense emissions across various wavelengths, from radio waves to X-rays. These AGNs are powered by the presence of a supermassive black hole at the galaxy's center, which is an extremely dense region of space where an enormous amount of mass is concentrated within a very small volume. When astronomers use sophisticated telescopes like the Hubble Space Telescope to observe the AGN, they observe a remarkable phenomenon. The AGN appears to have two distinct regions where light and other forms of radiation are emanating more intensely than in the surrounding spaces. The second point of focus, which is slightly off-center from the true galactic center, is the brighter concentration. Inside this region is the supermassive black hole, whose mass is estimated to be between 1.1 and 2.3 times 10 to the power of 8 solar masses, or about 110 to 230 million times the mass of the Sun's supermassive black holes are thought to be common in the centers of galaxies, including the Milky Way, and they play an important role in the dynamics and evolution of galaxies. When matter, like gas and stars, approaches a supermassive black hole, it forms an accretion disk around it. This disk of swirling material heats up and releases intense radiation, which is why AGNs are so bright. In the center of Andromeda, a supermassive black hole exerts a unique gravitational pull on surrounding stars, causing them to orbit it in an elliptical pattern resembling the orbits of planets around the Sun in our solar system. At a certain point in this orbit, called the perihelion, the stars approach the black hole closest. At this point, the gravitational forces are strongest, causing the stars to move at their highest speeds. As they bunch up, the stars release energy in the form of radiation, including visible light. The brighter point of concentration seen in Andromeda's AGN, which provides important hints about the gravitational dynamics and interactions between the supermassive black hole and the surrounding stars. Light and other types of electromagnetic radiation. The abundance of globular clusters, which are tight groups of stars that orbit around the galaxy's center like satellites orbiting a planet, is another intriguing feature of Andromeda. It is estimated that Andromeda harbors about 460 of these dense and ancient clusters, each containing hundreds of thousands to millions of stars that formed around the same time. The astounding number of globular clusters in Andromeda offers valuable insights into its cosmic history and its interactions with smaller galaxies over billions of years. This abundance suggests that Andromeda has been actively consuming smaller galactic companions in a process known as galactic cannibalism. As smaller galaxies come within Andromeda's gravitational reach, immense forces strip them of their stars and other components. The stars from these cannibalized galaxies become part of Andromeda's stellar population, adding to the rich diversity of stars present in the galaxy. This process of assembling stars and globular clusters from smaller galaxies is characteristic of spiral galaxies such as Andromeda. Spiral galaxies, distinguished by their disk-like form and characteristic spiral arms, offer an optimum environment for interactions and mergers with smaller companions. Recent analysis and observations have led astronomers to speculate that the Andromeda Galaxy may be undergoing an intriguing metamorphosis, evolving from a typical spiral galaxy to a relatively uncommon kind known as a ring galaxy. Ring galaxies are interesting and relatively uncommon celestial objects that are characterized by their circular or elliptical ring-like structures. The rings are made up of bright, young, blue stars, and the central region contains relatively little luminous matter. These distinctive features set ring galaxies apart from the wide variety of galactic structures. There are three main types of observed optical ring phenomena: nuclear rings, inner rings, and outer rings. Nuclear rings are found close to a galaxy's center, whereas inner and outer rings are farther out. There are also two main types of ring galaxies: O-type and P-type. O-type ring galaxies have centrally located nuclei, and their rings are smooth and regular in shape. P-type ring galaxies, on the other hand, have off-center nuclei, and their rings tend to be more irregular. Astronomers have proposed two main mechanisms for the formation of ring galaxies. 1. They can form when two or more galaxies collide. Or 2. A smaller galaxy passing through the center of a larger galaxy can cause the formation of a ring-like structure. Examples of ring galaxies thought to be formed through galactic collisions include the Cartwheel Galaxy, Galaxy Pair 2026-424, and ARP-147. Ring galaxies are considered rare cosmic gems. Only about 1 in 10,000 galaxies are classified as such. The most fascinating thing about Andromeda, though, is what is currently happening to it. According to scientific theories, the Milky Way galaxy and the Andromeda Galaxy are on a collision course and will eventually merge to form a new supergalaxy. This enormous event has already been given humorous nicknames like Milkomeda or Milk Drama, which are known worldwide. However, the implications of this merger for humanity would be devastating. As the two galaxies approach each other, their immense gravitational pull will cause them to distort one another's shapes, which will lead to tidal forces that will pull stars, gas, and dust between the galaxies. The galaxies will then begin to overlap, causing chaos and destruction everywhere, but not all at once. When the two galaxies get closer together, they collide, which starts the process of merging. Dust, gas clouds, and stars from both galaxies mix and interact, forming new structures and star clusters inside the newly formed galaxy. The merger causes major orbital changes in the stars, which make the environment chaotic and dynamic. Some stars may be thrown out of the new galaxy, while others settle into new, more elliptical orbits. At the center of both galaxies are supermassive black holes, which will eventually merge to form an even larger black hole at the center of the newly combined galaxy. The collision and subsequent merging of the galaxies will produce spectacular displays of star clusters, shock waves, and bright bursts of radiation. Totally new constellations and stellar arrangements will emerge, changing the sky as we know it. The merging process can also initiate bursts of star formation in areas where gas clouds collide and compress, creating new stellar nurseries. These nurseries become the birthplaces of young, massive stars that will shape the new galaxy. The Andromeda Galaxy and the Milky Way merger will alter Earth's environment dramatically. These changes could affect the biosphere, or the regions of Earth where life is found. These changes could disrupt habitats, alter biodiversity, and even cause local extinctions. The merging of galaxies could disrupt Earth's climate and weather patterns. Changes in temperature, precipitation, and weather events could occur globally, influencing the distribution of vegetation and animal habitats. The shift in solar radiation might affect vital processes for plant and animal life, possibly causing disruptions in ecosystems. The increase in cosmic radiation within the intergalactic region could affect Earth's atmosphere, including the ozone layer. These changes could affect climate patterns and have implications for the survival of various species. Existing habitats for different species may become less hospitable or shift completely as a result of climate change. Many animal species depend on specific migration patterns for reproduction, foraging, and survival. Changes in climate may disrupt these migration routes, making it difficult to find food, water, and suitable breeding sites. Competition for resources may increase, and new opportunities may present themselves for some species to thrive in the altered ecosystems. Regrettably, some species may not be able to adapt quickly enough to the new conditions, resulting in local extinctions. All of this is devastating, but the truth is that the collision process will not happen overnight. It is estimated that the collision will start about 4 billion years from now, and that it will take another 2 billion years to complete. As for humanity, we will be extinct by then, and Earth will have experienced significant changes long before the collision even happens. About 5 billion years from now, our Sun is estimated to evolve into a red giant, eventually expanding and engulfing the inner planets, including Earth. This process will probably make our solar system uninhabitable long before the two galaxies merge. If some descendants of our species or other life forms exist around 4 to 6 billion years from now, they will be extremely remote from us in evolutionary history, possibly nothing like humans today. The Andromeda Galaxy and the Milky Way merge, and as they do, cosmic forces and interactions between stars, gas, and dust will shape a new galactic structure unlike anything we've ever seen. The merger itself raises questions about the fate of our solar system within the new supergalaxy. There's a chance that our solar system could be ejected into the intergalactic medium during the collision. However, the exact outcome and structure of the new galaxy are impossible to predict with certainty. One likely consequence is that the galactic disks of both galaxies will be disrupted, and the spiral arms of each galaxy will be dispersed. Whether this means that Milkomeda becomes an elliptical galaxy or a large disk galaxy is something we won't know until the merger actually occurs. A star system with a planet orbiting in the habitable zone may exist within this merging galaxy. Conditions there might be favorable for liquid water to exist, which is an essential component for the emergence and maintenance of life on Earth. Nevertheless, the stability of the new galactic structure will be critical in determining whether life can flourish. Interactions between stars and possible gravitational disturbances may modify planetary orbits and environmental conditions, which in turn may impact the evolution and sustainability of life on any potential habitable planets. A merger of galaxies can result in increased cosmic radiation and stellar activity, including rare events like supernovae and gamma-ray bursts, but it is difficult to predict when these events will occur and how they will affect planetary environments. If life were to arise in the new galaxy, it would probably have to adapt to the particular conditions of its environment because the new galactic region would have different physical and chemical properties than Earth. But modern humans won't be able to exist in this new galaxy. Do you believe humanity will be able to adapt enough to survive in Milkomeda? Then share your opinions in the comments section below. If you like this video, then hit the like button. Until next time, we'll see you in another one.